Alrighty, we are, or I am back um, for our 12th office hour. After today, we only have 4 more of these, which is crazy. So yeah, I'm here. I'm available. So, hit me up with your questions. Let's see. Okay, Chapter 8 material. Practice problem. Yes, I sure can. Okay, yes. All of these things. We can do all of these things and more. Okay, so let's see. Okay. So I'm gonna write a I'm gonna write a couple concentration examples. And maybe I'll just like let them kind of float rather than working them immediately. I'll write these, give you a chance to do them, and then maybe we can circle back and work them together. Okay, and lecture on Tuesday. Give me 1 second, because I do not remember. Let's say it's Thursday. Off the top of my head. Okay, so let's see. It looks like Tuesday was percent volume. We get molarity stuff. Okay. Oh, yes, the exam caliber question. Yeah, totally. Okay, good. We've got some good questions like that. Okay, so Brianna, I'm gonna start by writing a few of these for you. So we have, let's say that we have a solution that is 16% mass to volume of calcium chloride. Oops. Yep, totally, Kate. I found the exact one you're talking about. So we've got a solution that's 16% mass to volume of calcium chloride. how many grams of calcium chloride are in 4.50 liters? Of solution. All right, there's one example. Another example, we'll start with the same concentration. %, mass to volume. Again, of calcium chloride. What is the molarity of this solution? All right, and then let's see. I kind of wanted to do 3, so we got plenty of reps in. Okay, let me think. So you have a solution that is 20.4% mass to mass of not sodium chloride, sodium fluoride. How many grams of solution contain 8.96 grams of sodium fluoride? All right, so here's kind of in triplicate some examples of concentration problems. So we will circle back to those and do them in a second. But first, let's hit up Parthana's question from chapter 7 in the textbook, number 86. Okay. All right, so let's take a look. Chapter 7, problem 86. Indicate whether each of the following statements concerning boiling point and boiling are true or false. All right, so the first one is a liquid can be made to boil at temperatures higher than its normal boiling point. And that is true. You can totally make a liquid boil at temperatures higher than its normal boiling point. Because, for example, you could add a solute. You could also change the pressure, right? If you increase the pressure, it'll boil at a higher boiling point. It's why when you go up in elevation, water boils at a lower temperature under than 100 degrees. So part A, totally true. Part B, a liquid can be made to boil at a temperature lower than its normal boiling point, also true. If you take a liquid to a higher elevation where the pressure is lower, it'll boil at a lower boiling point. So that is also tweakable. A, B, C. In a boiling liquid, the vapor formation occurs within the body of the liquid. And that one is false. The vapor formation occurs at the surface of the liquid, but not down in the body. That's where the liquid is. The vapor formation happens right at the surface. A, B, C, and D. To compare the boiling points of two different liquids to the external pressure. To compare the boiling point of two different liquids, the external pressure should be the same. And that is true. If you wanted to compare the boiling points of two liquids, you got to make sure that the external pressure is the same, because higher pressure means higher boiling point, lower pressure means lower boiling point. So if you have different boiling points, you can't compare those two together. All right, so that is the conceptual answers to the conceptual question. That is number 86 from chapter 7. Yes, we can, but we're gonna flip through these all in order. Okay, Kate, you wanted to see the exam caliber question from Tuesday's lecture. Yeah, so let's take a crack at this. So So this is the exam caliber question from a few days ago, and it says that first we're asked to balance a reaction where we have aqueous silver nitrates, silver 1 nitrate. So we've got silver. Nitrate is one of our polyatomic ions. So aqueous silver nitrate will look like so. Reacts with calcium chloride. All right, calcium is a charge of +2, chloride a charge of -1. So we're going to need 2 chlorides for each calcium. And then this produces silver chloride. Again, these pair up in a 1-to-1 ratio because positive 1, -1, and then aqueous calcium nitrite. And we need 2 nitrites to pair with calcium because of our charges, and so we have to put that in a parentheses because it is a polyatomic ion. All right, now at this moment in time, we've written out our reactants, we've written out our products, but now we need to balance our chemical equation. So we've got a lot of elements in play here. We've got silver, nitrogen, oxygen, calcium, and chlorine. Silver, nitrogen, oxygen, calcium, chlorine. On our reactant side, we have 1 silver, 1 nitrogen, 3 oxygen, 1 calcium, 2 chlorines. On our product side, we have 1 silver, 2 nitrogen, 6 oxygen, 1 calcium, 1 chlorine. So always go for what's easiest to balance our chlorines. We got to multiply our silver chloride by 2. Then to balance, so we now need to balance our silver, so we should multiply silver nitrate by 2. And you'll notice that not only does this balance silver, but it also balances nitrogen and oxygen in one fell swoop. So this is part A. We have balanced our chemical equation. In part B, we're told that we mix 25 milliliters. We're told that we have, well, first 0.001 molar concentration for each reactant, and that we mix 25.0 milliliters of each together. And we're asked to find the theoretical yield of the precipitate, which is silver chloride. All right. Now, something that I want to take a moment to talk about is this is something that you will see over and over and over again, where you're given a molarity and a volume. All right. Molarity and volume is it's super clutch to be given these two in tandem, because we know that molarity is equal to moles over liters, right? And so if you do a little bit of algebra and if you multiply both sides of this equation by our volume in liters, you get a new expression that tells you that moles, your number of moles, are equal to your molarity times your volume in liters. And so it is super common to be given in combination your molarity and a concentration, because these two things together allow you to find your moles. All right? And moles allow us to do stoichiometry. So we need to do this is a limiting reactant problem, right? We're given an initial quantity of both silver nitrate and calcium chloride. So we need to calculate how much precipitate could be made from silver nitrate, how much could be made from calcium chloride, and then whichever one's smaller, that'll be our theoretical yield. All right? And again, what allows us to get there is this equation here, the rearranged equation of molarity. Moles of solute are equal to your molarity times your volume in liters. One last thing that you'll notice before we start getting into it is both of these volumes have been given in milliliters, and to use this equation we need liters. So we need to do a quick unit conversion to get 25 milliliters to liters. So we put milliliters in the denominator, liters in the numerator, and 1 milliliter is 10 to the negative third liters. Milliliters cancel. So 25 milliliters is equal to 0.0250 liters. Again, we've got to keep the same number of sig figs. Okay, with that in mind, let's go ahead and solve this problem. All right, or at least part B of this problem. So it's going to start with our, I'll start with silver nitrate, 1.00. Now molarity is moles AgNO3 over liters. We multiply this by our volume in liters, 0.0250 liters, and you'll notice liters cancel with liters. We're left with moles of silver nitrate. Now, we want to convert from moles of silver nitrate to moles of silver chloride. And this unit conversion comes from the balanced chemical equation. 2 moles of silver nitrate will react to make 2 moles of silver chloride. So now moles of silver nitrate cancels. Our final unit conversion will take moles of silver chloride and convert it to grams. So now we got to look up some masses on the periodic table. Silver has an atomic mass of 107.87, and chloride 35.45. Adding these together, yep, and then let's see, I did that in my brain. I'm just going to double check. Oops. 107.87 plus 35.45. Okay, yep, I did it right in my head. So now this is our molecular mass. And now we're good. Oh gosh. Sorry, that was allowed to crunch our numbers. So we have 1 times 0.025 times 2 divided by 2 times 143.32. Gives us, and we can keep 3 sig figs, 3.58 grams of precipitate. All right. Now we don't know if this is our answer. We need to calculate with our starting quantity of our other reactant and see which is smaller. All right. So let's take 1.00 moles of calcium chloride over liters and multiply this by our volume. All right, and again, liters cancel liters. Next, we need to cancel moles of calcium chloride. And convert it to moles of silver chloride. Now here, the balanced chemical equation tells us 1 mole of calcium chloride produces 2 moles of silver chloride. Moles of calcium chloride cancel. And then finally, our last conversion, we'll take moles of silver chloride to grams. Moles of silver chloride cancel. And now we crunch our numbers for a second time. So 1 times 0.025 times 2 times 143.32. And this comes out to be 7.17. And as we know, our theoretical yield is the smaller of the two numbers. So that is our theoretical yield. All right? Now, that we have our theoretical yield, we can solve our final step. We're told that our percent yield is 87.3%, and we know that percent yield is actual over theoretical times 100. We just found our theoretical yield, right, in the previous step. So we can solve for actual. 87.3 is equal to actual yield over, where was that? 3.58 grams of silver chloride times 100. So we want to multiply both sides by 3.58 grams over 100. Cancel on this side. So we get our actual yield is equal to 3.58 grams of silver chloride times 100. Oh, sorry, no, not times 100. Times 87.3 over 100. So we have 3.58 times 87.3 divided by 100. So our actual yield is 3.13 grams. That is the correct answer with the correct sig figs and the correct units. All right, so that is the exam caliber question from lecture last Tuesday. All right, we have another chapter 7 problem. Number 35, part C. So let's take a look. 35, part C. So we're told that a sample, of course, you are welcome, Kate. A sample of carbon dioxide gas has a volume. All right, so I'm just going to start writing down stuff. We've got a volume of 15.2 liters at a pressure of 1.35 atmospheres and a temperature of 33 degrees Celsius, which I am going to compulsively convert to Kelvin. So it's 306 K. All right, part, and then it says, determine the following for this gas sample, and part C says they want us to find the temperature. Interesting. The temperature in degrees Celsius at a pressure of 735 millimeters of mercury and oh wait, no, I wrote this from the wrong thing. At a pressure of 325, excuse me. Oh wait, no, I'm just looking at the wrong problem entirely. Sorry, give me 1 second here. What was I looking at? I don't even know. Oh, hang on. No, they do. I'm sorry. I jumped from 35 to 33. They do want us to find the temperature in Celsius. I'm going to leave my finger here. And they give us a pressure of 7.00 atmospheres and a volume of 0.973 liters. All right, so the thing to notice is this is V1, P1, and T1. This is T2, P2, and V2. You'll notice here that moles are missing. It's because in this problem, they're constants. All right, so they just drop out. We're dealing here with the combined gas law. P1 V1 over T1 N1 equals P2 V2 over T2 N2 and as we've already discussed, moles are constant. Oops. Moles are constant, so they cancel. And we have been given our initial pressure, volume, and temperature. We've been given our final pressure and volume. We need to find temperature. All right, so since temperature is what we're trying to find, we need to get it out of our denominator, right? So for starters, we're going to multiply both sides by our final temperature. That way it cancels out of this denominator. This gives us T2 times P1 V1 over T1 is equal to P2 V2. I feel like these could all be droids from Star Wars, right? R2D2. P2 V2. And now we need to isolate our final temperature on one side of this equation. So we got to multiply both sides by T1 over P1 times V1. All right, and here everything cancels off of the left side of this equation. And we get T2 is equal to P2 V2 T1 over P1 V1. All right. Now we have all the numbers here, so we can plug these in. Our final pressure is 7.00 atmospheres. Our final volume is 0.973 liters. Our initial temperature is 306 Kelvin. And even though we were asked to find our temperature in degrees C, whenever you're using the combined gas law, you must convert it to Kelvin. So it's kind of irritating. We got to convert it to Kelvin, and then after this is all said and done, we're going to have to convert it back. But you always convert to Kelvin when you're using the ideal gas law. P1 is 1.35 atmospheres, and V1 is 15.2 liters. Now you'll notice liters cancel liters, atmospheres cancel atmospheres, and which is good, right? We want a temperature unit left over. So T2 will be equal to 7.00 times 0.973 times 306 divided by 1.35 divided by 15.2 2. Our temperature comes out to be 101.56754 Kelvin. But we can only keep 3 of these sig figs. So 1, 2, 3. And this 5 will round up. So cracking open a new slide, our temperature will be 102 Kelvin. They want to know what this is in degrees Celsius. When you go from Celsius to Kelvin, you add 273. When you go from Kelvin to Celsius, you subtract. So we have 102 minus 273. And our final temperature then is negative 171 degrees Celsius. So that is this was chapter 7. Way of recap. Number 35, part C. Could you have not multiplied 1 over... Okay. Esther. Great question. All right. So Esther is wondering, oops. Let's write up the equation. So Esther's question is, can't you just multiply 1 over P2 V2 on both sides? And I mean, the short answer is you can do whatever algebra you want. As long as you do all the algebra correctly, things will be fine. But notice something. So they cancel over here. And so on the left side of the equation, you get P1 over, V1, P1 times V1 over P2 V2 times T1. But what does that equal? That does not equal your final temperature. It equals 1 over your final temperature. So to solve this problem, you've got to get this guy out of the denominator somehow. All right, so you could start by dividing both sides by P2 times V2, but you still have to get this T2 out of the denominator, and when you flip it, it'll be the final form of the equation will be the one that we used. So it's important to remember that you can never leave the variable you're solving for in the denominator. It has to be isolated on one side and in the numerator. So you could do that as your first step, but you still have more algebra ahead is the answer. Yep. But you see, Esther, you could totally do the reciprocal. So check this out. Yep, you need the reciprocal, but this might be an easier algebraic way to do it, because if you take the reciprocal, right, and you flip numerator and denominator here and then do the same thing there, what do you get? You get P2 V2 T1 over P1 V1 is equal to just T2, right? T2 over 1. And this is the form of the equation that my algebraic steps led me to. So doing it that way is totally valid. You just can't stop with T2 in the denominator. But take the reciprocal, flip everything around, and you got to the exact same place that I did. We climbed the same mountain, but from different sides. Algebra is a beautiful thing. Okay. Let's see. Sorry. I don't think anybody has the right to get that excited over algebraic manipulation, let alone me. All right. Parthana, you wanted to know about 92 and 96. And then at some point, Brianna, I haven't forgotten about the problems that I gave you. Let me know. I'm going to do 92 and 96 here. But, oops. Brianna, let me know when you would like to see any of those examples. Yep, totally. You were off to a strong start. You just had one algebraic step left, Esther. Okay. Okay, awesome. I'm glad it's helpful. Let's see. Okay, so 92. Grants, I see your questions were slowly chugging away. We'll get there in just a bit. This is chapter 7. 92. Whoops, part C. Awesome. Let's see. So 92C. Indicate whether or not each of the following statements about intermolecular forces, okay, so you have C and D, is true it's true or false. So C, one of the atoms participating in hydrogen bonding must possess a non-bonding pair of electrons. Totally true. One of the two molecules participating in hydrogen bonding must have a lone pair. Otherwise, no hydrogen bond can form. So A, B, C, and then D. Let's see. Both molecules participating in dipole-dipole interactions must be polar molecules. Totally true. If you are not a polar molecule, then you are not engaging in dipole-dipole forces. This is not dipole-dipole attraction. That only happens between polar molecules. So C and D for 92 are true. Let's see, 90. Let's take a look at 96. So chapter 7, number 96, part D. For liquid samples of the following diatomic molecules, indicate the type or types of intermolecular forces present. There may be more than one correct answered. So part D is they want us to determine the intermolecular forces for BRCl. Okay, so first off, whenever someone asks, and that someone's going to be me, let's be real, whenever I ask you what intermolecular forces are present in a molecule, you always put London dispersion, because everything experiences London dispersion forces. Everything with electrons experiences London dispersion forces. Let's get back a little bit. I'm looking for the electronegativity periodic table. Okay, so as far as electronegativity is concerned, bromine is 2.8, chlorine is 3.0. All right, so our difference here in electronegativity is 3.0 minus 2.8. So that difference is 0.2. This electronegativity means that this bond is non-polar. And if your bond is nonpolar, your molecule is nonpolar. So there's no dipole-dipole here. And there's no hydrogens, so you can't hydrogen bond. So London dispersion is the only intermolecular force at play in bromine monochloride. It is just dipole-dipole. Okay, let's see where we are. Okay. Lab 8. Prelab question 2. Let me pull up Lab 8 first. Okay, let's see. Determination of the universal gas law, Prelab question 2. Okay. And then 2B. Okay, and then, sorry, I'm just reading. I know there's a string of these questions related to Lab 8. Okay, so Carinza, you totally do use the mass of the magnesium strip, the moles of magnesium reacted. You're going to use the moles of magnesium in combination with the balanced chemical equation. So you're going to use both of those together to find, for example, moles of hydrogen gas. Now let's look at this pre-lab question 2. A, B, and C are all kind of connected, all right? So in this first part, you got to understand part A to do part B and then part C. So in this experiment, the partial pressure of water is subtracted from the total pressure of the gas contained in the collecting tube. What would happen to the pressure value if this were not done? All right, so the pressure of hydrogen is equal to the total atmospheric pressure minus the vapor pressure of water. All right, that's what the partial pressure of hydrogen is equal to. All right, then right here, if you do not subtract the vapor pressure, then the value of your partial pressure of hydrogen will be too high, right? If you don't subtract it, then the value you're going to be using is going to be higher than what the real thing is. All right? So that's part A. Part B, explain how the value you calculate for the molar volume of hydrogen would be affected. All right? Now, molar volume is equal to volume divided by moles. All right? And you can actually get a equation for molar volume from the ideal gas law. All right? If you take the ideal gas law and you divide both sides by moles and pressure, Watch what happens. On the left side of the equation, pressure cancels. On the right side of the equation, moles cancel. And so this gives you an equation for molar volume, right? Volume over moles is equal to R, ideal gas constant, times temperature divided by pressure. So since the molar volume equals RT over P, oh wait, hang on. RT over P. They're asking how the value you calculate for the molar volume of hydrogen would be affected by this. Well, we already know from part A, if you don't subtract your vapor pressure, that the partial pressure is too large. Right? That partial pressure is too large. When your denominator is too large, if the denominator is too large, then the value for molar volume will be too small. It'll be too small. So that is part B. Part C, let's see, explain how the value you calculated for R would be affected. All right, so again, we're going to do a little bit of algebra. If you look at the ideal gas law, whoops. PV equals nRT. If we do some algebra and we isolate R on one side of the equation, so that moles cancel, temperature cancels, and we get R is equal to PV over NT. Now, I'm going to rearrange this just a little bit. I'm going to call it P over T times, then I'm going to put this in a parentheses, V over N, and then I'm going to rearrange it one more time. P times V over N is equal to T. All right, because this is the partial pressure of H2, and this is the molar volume. All right, now I'm going to take this equation and rewrite it over here. Ideal gas law is equal to P times partial pressure of hydrogen times the molar volume of hydrogen over T. When you look at this expression, we know that pressure this is too large. But this, this is too small. So, of the three quantities we're using, one is too big, one is too small, the other one's right. Now, we don't know, will they be just enough to cancel out? Will it still lean one way or another? It's unclear. But what is clear is the value for the ideal gas constant will likely be incorrect. You might get lucky and maybe one is just the same amount bigger as the other one's the same amount smaller, but you don't know that they'll compensate for each other. So it will likely be incorrect because 2/3 of the numbers that they're using in this calculation are off, have wrong values. So that is how I would answer the Prelab question number 2, lab 8. All right. Whoa. It says my thing wasn't sent. There we go. Okay. All right, Brianna, you have been waiting patiently. Let's circle back and do those examples that I wrote up right at the beginning. All right, and then let me just make sure I know where we are. All right, and then we'll come back, Parthenize, to see all your chapter 8 questions, and we'll get to everything eventually. All right, but I'm at my breaking point. These headphones are fine for an 80-minute lecture, but I find after like the first hour of office hours, my ears need a break. Okay. So let's see. Oh, right. We're doing these problems. So our first example, we're told that we have a 16.0% mass to volume solution, calcium chloride. We're asked to find the grams of calcium chloride in 4.50 liters. All right, and this really boils down to remembering what mass to volume is. This means that we have two ratios at our disposal. 16.0 grams of calcium chloride in 100 milliliters of solution, Or you could write it like this: 100 milliliters of solution over 16.0 grams of calcium chloride, whatever helps you out. Now, you'll notice here that we want to know grams of calcium chloride, and we have volume in the denominator, but our volumes are different units. So we need to, before we can multiply this by our volume, we need to do a unit conversion to figure out to convert our milliliters into liters. All right, so first off, 1 milliliter is 10 to the negative third liters. Now milliliters cancel, and now we can multiply this by our volume in liters. Right, liters cancel liters, and now we can crunch our numbers. 16.0 divided by 100 divided by 10 to the negative third times 4.50. So my calculator is telling me that my answer is 720 grams, but I need to look at my sig figs. My volume had 3 sig figs, my percent mass had 3 sig figs. My answer needs 3 sig figs, but it only has 2 right now. So I need to write this in scientific notation. 7.20 times 10 to the squared, 10 to the times 10 squared grams of calcium chloride. All right, that is the mass of calcium chloride in 4.5 liters of solution. Sorry, I'm just checking my feed. Okay, I thought so. My live chat stopped updating. There we go. Okay. We're back in business there. Okay. Okay, so that's the first one. Let's look at number 2. Number 2, we're told that again, we're dealing with our 16.0% mass to volume solution of calcium chloride, and we're asked to find the molarity. All right, now again, this is 16.0 grams of calcium chloride in 100 milliliters. That's what that percentage means. We want to find molarity, which is moles of calcium chloride per liter. So what we need to do is we need to convert our denominator volume unit to liters, and we need to convert our numerator mass unit to moles. All right, that's how we solve this problem. So setting this up, we can convert our numerator from grams to moles using the molecular mass of calcium. All right, calcium has an atomic mass of 40 point something, 40.08. Chlorine is 35.45, and we have two of them in this molecule. So this, let's see, crunching our numbers, will be 35.45 times 2 plus 40.08 is 110.98 grams per mole. Our second unit conversion needs to convert from milliliters to liters, and as we know, 1 milliliter is 10 to the negative third liters. So milliliters cancel milliliters, grams cancel grams, and now we're good to crunch our numbers. 16.0 divided by 100 divided by 110.98 divided by 10 to the negative third comes out to be, let's see, we can keep 3 sig figs? Yeah, 3 sig figs. 1.44 moles of calcium chloride per liter. That is the same thing as 1.44 molar of calcium chloride. So that is the answer for the second example. Yes. Okay, and then the last of the 3 examples I wrote up at the beginning of office hours. We have a 20.4% mass to mass. Oops. Of sodium fluoride, and we're asked to find the grams of solution that contain 8.96 grams of solute. Now again, I'm going to pull this trick. This 20.4, that means that you have 20.4 grams of sodium fluoride in 100 grams of solution. Or you could also use 100 grams of solution per 20.4 grams of sodium fluoride. Both are totally valid. Use whichever one's easier, more convenient, and here the second one's going to be more convenient. If we multiply this second ratio by 8.96 grams of sodium fluoride, right, over 1, grams of sodium fluoride cancels, and what are we left with? The exact unit we want for our answer. So 100 divided by 20.4 times 8.96. We can keep 3 sig figs, so 8.96 grams of sodium fluoride will be contained in 43.9 grams of solution. All right, and that brings to a conclusion my trio of examples. All right, let's see. I know there's been a flurry of communication. Let's see where I left off. Okay. Still at the beginning of the comments feed. We will get to it all. Chapter 8. Parthana, you've got a slew of questions from Chapter 8. Let's take a look at them. Didn't drop it. Though I almost did. So this is... Oops. Chapter 8. Question number 2. B and C. Okay. Indicate whether each of the following statements about general properties of solutions is true or false. For solution formation to occur, the solute and solvent must chemically react with each other. False. They have to interact with each other, but they do not have to react. Actually, all solubility solution is a physical change, not a chemical change. So if they're reacting, they're actually not, it's not getting dissolved. Something else is happening. So A, B, C. Solutes are present as individual particles in a solution. I don't understand the question. So I'm just going to say true. There are individual particles floating around in solution. I mean, they're kind of connected, kind of hanging out with other solvent molecules, but I'll just say true. Not entirely sure what they're asking. All right, so that was Chapter 8, number 2. How about Chapter 8, number 6? This is 6B. For each of the following pairs of solutions, select the solution with for which solubility is greatest. All right, and we're told that we have nitrogen gas in water, where pressure is 2 atmospheres and temperature is 50 degrees Celsius. And the second one, still nitrogen in water, where the pressure is 1 atmosphere and the temperature is 70. All right, here's the key to this one. Gaseous solutes are more soluble at high pressure and low temperature. So that means that the first solution, which has twice the pressure, and a cooler temperature will have a higher concentration of solute. All right, number 8. Classify each. Let's see here. Chapter 8, number 8. Classify each of the following solutions as saturated, unsaturated, or supersaturated based on the following observations made after adding a small piece of solid solute to the solution. So part A, the added solute dissolves rapidly. Well, if it rapidly dissolves, that means that the solution was unsaturated. Right? Because if it were saturated, more wouldn't dissolve. Part B, the added solute falls to the bottom of the container where it remains without any decrease in size. Well, if no more is being dissolved, then that means that the solution was saturated. Right? Can't hold any more. A, B, C. The added solute falls to the bottom of the container where it decreases in size for several hours, and thereafter its size remains constant. Well, since some dissolved, that means the solution was unsaturated to begin with. And again, they're asking about the solution before the solute was added. So if some of it dissolves, before adding that solute, it was unsaturated. And then D, the added solute causes the production of large amounts of solid white crystals. This is whenever you agitate a solution and all of a sudden precipitate starts coming out, that is an indication that it was supersaturated. But we didn't really go over that in class in that much depth, so you don't need to worry about me testing you on a scenario like Part D. So Part D, you can feel safe from Part D. Okay, let's see here. Chapter 8. Number 9, Part B. A solution made by dissolving 34 grams of sodium chloride in 100 grams of water at 0 degrees. Based on the data table 8.1, should this solution be characterized as saturated or unsaturated, dilute or concentrated? So let's take a look at table 8.1. Because I don't know what's in table 8.1 off the top of my head. So table 8.1 gives us the solubility of a bunch of ionic compounds at 0, 50, and 100 degrees C. We have a sodium chloride. So at 0 degrees Celsius, you can fit 35.7 grams of NaCl in 100 grams of water. So for part A of this problem, because again, remember we put, what was that? 34.0 grams in 100 grams of water. So this would be unsaturated. Right, it would be unsaturated, but Part B, they want to know, is this concentrated or dilute? We would say that this is concentrated because it is very close to the maximum amount of solute that can be dissolved. Right? These two are very close. And so we would say it is a concentrated solution of sodium chloride because you're near the maximum amount that can be dissolved. All right. Chapter 8, problem 10b. Okay. Let's see, 10b. Okay, so it looks like we're going to have to pop back to table 8.1. Too bad I didn't move my finger there. Okay. So we have put 0.455 grams of lead 2 bromide in 100 grams of water. And our trusty table 8.1, let's see, what temperature are we talking about? This is at 50. At 50 degrees Celsius, you can fit 1.94 grams of lead 2 bromide in 100 grams of water. So part B wants to know, is this concentrated or dilute? When you look at these two, this is 25% of the maximum amount. So I would say dilute. I would say that is dilute. All right, we're almost done with this barrage of problems. Let's see, number 16. Part C and D. Indicate whether each of the following actions will increase or decrease the rate of dissolving, table salt in water. So part C, heating the table salt prior to adding it to water. Well, we know that increasing temperature allows solutes to dissolve faster. So heating up would increase. Not as much as if you were heating up the solvent, but it'll still increase the rate. Now D, crushing a sugar cube to give it granulated form of sugar. This will also increase it. If you increase the surface area of a solid, you will increase the rate at which it dissolves. So both of those increase. All right, and then we have number 30, and then we get to change pace a little bit. I need to find the next question. Number 30. A compound has solubility of 750 milligrams per liter in water at 25 degrees C. Should this compound be characterized as soluble or insoluble? Okay, so this is number 30, by the way. So we're given the solubility. Solubility of a compound is 750 milligrams per liter at 25 degrees Celsius. To answer that question, let's see. I'm just looking in the book to see if they give us any sort of parameters for a question like this. It doesn't really look like they do. So, let's do a unit conversion. So this is milligrams per liter. Let's convert this to grams per milliliter. Maybe this will help us make a more informed decision. 1 milligram is 10 to the negative third grams. You'll notice liters cancel and milligrams cancel. So this means that we get 0.00075 grams in 1 milliliter. All right. Let's take a look at in 100 milliliters. So we take 0.00075 grams per milliliter, and we multiply this by 100 milliliters. That means you will get 0.075 grams in 100 milliliters. This means that you have a solution, saturated solution, will have a 0.075% mass to volume. That doesn't look very soluble to me. I would call this insoluble. Or what are they asking for in problem 30? Soluble or insoluble? I'd call this insoluble because if you look at the table, lead 2 bromide, which is considered insoluble, has a percent mass to volume of 1.94, and this is smaller than that. So that's what I would call insoluble. Now here's a question: am I going to ask you to make judgment calls on would you call this dilute or concentrated? Would you call this insoluble or insoluble? Soluble or insoluble? I wouldn't ask you to do that in a testing situation because it is a little subjective. Because the book doesn't give you clear guidelines of like, this is the threshold of what's considered insoluble. So I'm not going to test you on stuff like this, but I thought these were good problems because I thought they were thought-provoking. Let's see. So should it be above what? Right. Okay. Brianna, I totally can, but I just want to don't want to lose my place in line. Okay. Let's see. So we got that one under our belt. We did the lab 8 stuff. Let's see. Practice homework, chapter 7, number 25 is next up. Kate, thank you for waiting patiently. I know you asked this problem a little while ago. Let's see. So this is chapter 7, number 25. At atmospheric pressure, a sample of H2 gas has a volume. Okay, so I'm just going to start writing things. We got a volume of 2.73 liters. We got a temperature of 27 degrees Celsius. Just going to convert to Kelvin. It's 300 Kelvin, but it's actually 3.00 times 10 squared. Tell the right sig figs. What volume? So we're being asked to find the volume in liters. Will the gas occupy if the temperature is increased to 127? So again, converting that to Kelvin with the right number of sig figs, lands us here. Now, we're dealing with, whoops. Combined gas law. But pressure and moles are constant. So, pressure cancels, moles cancel, and now we need to solve for our final volume, so we should multiply both sides by our final temperature. So we get V2 is equal to T2 V1 over T1. T2 is 4.00 times 10 squared Kelvin times our volume of 2.73 liters over our initial temperature 3.00 percent squared Kelvin. Kelvin cancels, and now we can crunch our numbers. Okay. Okay, I'm going to crunch these numbers and then I'm going to get back and answer your sig fig questions. So stay on the line. So we got 3.6, 4 liters. So this is our final volume. Okay. So, okay, Kate, let me look. Confused on converting from Celsius to Kelvin. What do you do about sig figs when you have zeros in the mix? Why do you keep the 2 zeros behind the decimal since it's usually... Okay, Kate, great batch of questions. Let's look at what happens. So to convert degrees C to Kelvin, you add 273. All right, so you add 273. So for example, if you had 15 degrees Celsius and you wanted to know, no, don't be sorry at all. These are excellent questions. So if you wanted to convert 15 degrees Celsius to Kelvin, you just have to add 273. All right, now when you do, the value that you're going to get is 288. Now we're in Kelvin, but we still have to deal with sig figs. And when you look at it, 15 has its last significant digit in the ones place. 273 has its last significant digit in the ones place. So our answer must have its last significant digit in the ones place, and it does. So for this one, we're golden. But watch what happens when you add or when you convert 27 degrees Celsius to Kelvin. All right. 27 plus 273 is, the answer or value is 300 Kelvin. But now we have to look at the sig figs. The last sig fig in 27 is in the ones place. The last sig fig in 273 is in the ones place. Here's the thing. The last significant digit for our answer needs to be in the ones place, but it's not. 300's last significant digit is in the hundreds place. So the only way to get our last significant digit in the place where it needs to be is to write this answer in scientific notation. All right, scientific notation. To write 300 in scientific notation, you take the decimal and you bounce it till it's right behind the first sig fig in the number. All right? So we're going to write this as 3, and now we need to add 0.00. Now our last sig fig is in the correct place, times 10 to the second power Kelvin. All right, so the reason in this last problem that we worked, the reason why we had those 3.00 times 10 squared and 4.00 times 10 squared is we needed to write 300 Kelvin with its last significant digit in the ones place. The only way to do that is with scientific notation. So let me know if that makes sense. Okay, Brianna, you want to see an example that's similar to where was that? Homework 7, problem 17. Let me see if I can adapt one. Okay, I can totally adapt a problem. Okay, so this is similar to homework 7, number 17. Okay, awesome. Prince, I'm just about to get to where your questions on the Lab 8 stuff start showing up in the stack. I just got to finish this one from Brianna, and then we'll hit all your Chapter 8 stuff. All right, so calculate the molarity of a solution, or I should say calculate the molarity after 30.0 milliliters milliliters of water. Are added to 25 milliliters of 0.212 molar HCl. All right, so here, this is a dilution problem, right? We're adding water to a solution, and the dilution equation is M1 times V1 equals M2 times V2. And you'll notice that we're given M1, right, we're told our initial concentration. We're given V1, it's right here. We're asked to find M2, but we're not given V2. V2 is not 30 milliliters. V2 is actually the sum of the initial volume, 25.0 milliliters, plus the 30 milliliters of water you added. So our final volume is actually 55.0 milliliters. And now we have V2, and we can solve for M2 once we isolate it. So M2, our final molarity, is equal to M1 V1 over V2. Molarity is 0.212, our initial molarity. Our initial volume is 25.0, and our final volume is 55. Whoa. .0. Milliliters cancel. 0.212 times 25 divided by 55 is 0.0, let's see, we can have 3 sig figs, 964 molar HCl. So that is a problem similar to homework 7, number 17. With dilution problems, you will always end up using M1 V1 equals M2 V2, but how you use it can change. Based on how the problem is worded. Kate, sorry, I'm just now seeing your thing. Not always. Okay, Corinne, so let's see. So for the volume of hydrogen gas produced, give me 1 second, I gotta pull up the thing. I think, and Corinne, so give me 1 second to, I think they give it to you in the spreadsheet, but let me just pull up the data. Okay. Let's see. I'm making sure that I didn't miss any of your questions up here. Okay, there we go. Okay, there's a Esther, this is a long delayed answer. Um, okay, let's see. Kate, great question. All right. Anytime. Let's see, how picky... I mean, let me take a look at the problem. Off the cuff, I just tend to say very picky, but wait, regarding sig figs for Canvas homework 7, number 7. Today's, hey, every day, live every day as sig fig day, are words I live by. So when I look at number 7, here's the good news. Well, here. I'm not going to solve the problem, but they want to know, I want to know, how many grams of sodium hydroxide are in 9 mils of 8.0% mass to volume. And the answers which these all get jumbled every time anyway. Are as so. And so, whoops, not 8.8, it's, I think it's 8.0. So when I look at the sig figs, okay, because just to finish this thought, 2 here, we're doing multiplication, and all of these answers have 2, so I was like, well, all the sig figs are right for this problem. Okay, hang on. Let's pull up homework 6, because that was from homework 7. Homework 6, number 7. Okay, give me 1 second. Kate, I'm glad you asked this question. Just give me a minute to check something out. Oops. Oops. Okay. So, Kate, you're gonna like my answer. For this problem, don't actually okay. You're welcome, and great question. Okay, Kate Weber, this time around. How do you find partial pressure of something? Okay, totally, great question. So, for Lab 8, or let me stick this up here. They give you an atmospheric pressure. All right, and this is the atmospheric pressure, which I'm going to call total pressure, is equal to the partial pressure of hydrogen plus the vapor pressure of water. So when they ask you to find the partial pressure of hydrogen, you can do that if you subtract the vapor pressure of water from both sides of this equation. So whoa, hang on, there we go. So the atmospheric pressure minus the vapor pressure of water equals the partial pressure of hydrogen gas. That's how you go about doing it. All right, Carenza. Okay, seriously having trouble with the moles of hydrogen produced. Okay, yep, totally could. Okay, so here's the deal. Let me just make sure. Oh wait, no, I know the equation. So this is more Lab 8. All right, so we have a balanced chemical equation, right? Magnesium reacting with hydrochloric acid to produce hydrogen gas. So this is solid, this is aqueous, this is a gas, and magnesium chloride, which is aqueous. All right, now they tell us, so for example, here, let me just pull up. So for example, they tell us that we have 0.23 grams of magnesium that reacts, and we want to find out how many moles of hydrogen. So the way you set it up is you take your mass of magnesium, and then we're going to use the atomic mass, the grams of magnesium per mole, to convert from grams to moles, and magnesium is like 24 point something. 24.31. You grab that off the periodic table. Grams of magnesium cancel grams of magnesium. And then next, you use the balanced chemical equation to convert from moles of magnesium to moles of H2. And here in this balanced chemical equation, we've got 1 mole of magnesium produces 1 mole of H2 gas. Moles of magnesium cancel, and your answer will be the moles of H2 gas produced. So that's and they have these for 2 trials. This is the mass from trial 1. You can also do it with the mass from trial 2, and that is how you get there. Peeps are dropping. Totally. Absolutely anytime. Let's see. So here, yeah. Check this out. Okay, so still doing some lab 8 stuff. So we you already saw me go through the derivation that the partial pressure of hydrogen is equal to the total pressure minus the vapor pressure of water. So just pulling things, our total pressure, atmospheric pressure, was 765.6 millimeters of mercury. And then the vapor pressure of water was 21.1 millimeters of mercury. So when we take the difference here, we got 765.6 minus 21.1. So the partial pressure of hydrogen is 744.5, and that may seem like a lot, but remember, our units here are millimeters of mercury. Quick note, last sig fig has to be in the first decimal place, and it is, so we're good. Yeah. You're actually. You're actually spot on. It feels big because the units are weird, but check this out. If you convert from millimeters of mercury to atmospheres, oh, totally. Okay, good. That's serendipitous. When you convert from millimeters of mercury to atmospheres, and this is an exact conversion. Millimeters of mercury cancel. You divide by 760, and then your answer comes out to be 0.9796 ATM, which is a totally normal atmospheric pressure. Yeah, totally. It's good that you have that intuition of like, whoa, I've never seen a pressure unit as high as 700, or pressure as high as 700. But then when you convert the units, it actually isn't that crazy. Yep, totally. And then Kate, I'm sure you saw that the total pressure was the atmospheric pressure for today. And so so that is the ideal gas constant. Yep, totally. Okay. So for R, so calculating R, they don't just want you to put the value of R that we know it is. They will actually want you to use the ideal gas law and the quantities that get measured in this lab for you to calculate a value for R based on those values. So moles canceling moles, temperature canceling temperature. You get an equation R is equal to PV over NT. And then molar volume is just volume divided by moles. Let's see, can I show you how to do 8, 5? I totally can. All right, let's see. 8, 5. From the textbook. Let's see. Oh, there we go. Oh, there we go. That is exact. I was just about to ask what question. Okay, so let's take a look here. So this is quick. Quiz 8, 5, number 4, from the textbook. On page 217. Okay, number 4. The number of grams of sodium chloride present in 10 grams of a 1% mass-to-mass sodium chloride solution is... Okay, so we're told that we have a 1.00% mass-to-mass solution of sodium chloride. And they tell us that we have, 10 grams of solution. And they want to know how many grams of just sodium chloride we have. So, again, remember what this means. It means that you have 1.00 grams of sodium chloride in 100 grams of solution. So if you want, so notice we've been asked to find our mass of sodium chloride, and we've been given our grams of solution. So if you multiply this thing by 10.0 grams of solution over 1, grams of solution cancel, and so we have 1 divided by 100 times 10 gives us, let's see if we can have 3 sig figs, 0.100 grams of sodium chloride. Okay. Yeah. Okay. Let's see. Okay. So here's kind of the breakdown of Karenza's question. Oh, there we go. So if you want to use PV equals nRT, the thing that limits you usually is the ideal gas constant, because the ideal gas constant is equal to 0.0821 liter atmospheres per mole Kelvin. So the unit up here of pressure is atmospheres. So if you have a pressure, let's say, of 753 millimeters of mercury, before you can plug it into the ideal gas law, you need to convert millimeters of mercury into atmospheres. That way they'll cancel with the pressure unit that the ideal gas constant has. So the unit conversion is 1 atmosphere is 760 millimeters of mercury. 753 divided by 760 is 0.991 atmospheres. And now that your units are consistent with the units in the ideal gas constant, now you can use this pressure with PV equals nRT. Yeah, you do the Oh, no. Gotcha. Awesome. Yep. Current, that is exactly it. Ah. Let's see. All right, let's check this out. Oh, chapter 7, sorry. Chapter 7. Number 65. No, chapter 7, number 65. Let's see. Changes of state. Okay, so here we need to indicate whether or not both members of each of the following physical state changes have the same thermicity, both exothermic or endothermic. Okay, so exothermic means that energy is released. In other words, you move from high to low. And endothermic is the opposite. With an endothermic process, energy is absorbed. And this happens when you move from low energy to high. All right. So with this in mind, let's look at the pairs. So so for part A, they say evaporating. And freezing. All right, so evaporating is moving from, let's see, if we're evaporating, we're going from liquid to gas. Gas phase is high. And this is liquid phase is low. So if you're moving from low to high, that makes this endothermic. All right, now let's look at freezing. Freezing, you're moving from the liquid phase to the solid phase. Liquid phase is higher in energy than the solid phase, so this is high. This is low. So if you're moving from high to low, you're exothermic. All right, so A does not have the same thermicity. These two do not have the same thermicity. Let's look at B. All right. So B, melting. Melting and was it? Oh, and deposition. Melting and deposition. So for melting, you're going from what? Melting, start as a solid, go to a liquid. All right, solid is lower energy than a liquid, so here you're moving from a low energy state to a high energy state. So if you're going from low to high, this would be an endothermic process. If we're talking about deposition, deposition is going from the gas phase to the solid phase. Gas is higher in energy than solid. So here we're going high to low. High to low means the process is exothermic. All right, so B, these two processes do not have the same thermicity. One is endothermic, one is exothermic. Let's look at C. Freezing and condensation. When we talk about freezing, we're talking about going from the liquid phase to the solid phase. Liquid is higher in energy than solid, so if we're going high to low, high to low means that this process will be exothermic. And then if we're talking about condensation, condensation is going from the gas phase to the liquid phase. Gas is higher in energy than liquid. So again, we're going high to low, so this will also be exothermic. So C is our first example of two processes having the same thermicity. Let's see now part D. Part D, we're doing deposition and condensation. For deposition, you're going from, oh, sorry, this is part D for 65. Give me one sec here. Sublimation and evaporation. Sublimation takes us from the solid phase to the gas phase. Solids are lower in energy than gases, so we're going low to high. Which makes this endothermic. And then for evaporation, we're going from the liquid phase to the gas phase. The liquid phase is low in energy. The gas phase is high in energy. And again, moving low to high, this is also endothermic. So sublimation and evaporation would have the same thermicity. And so yeah, so D and C have the same thermicity, A and B have opposite thermicities. All right, it is 6:11. We went a little bit over today, but that's all right. let's see. But this is where we're gonna put a pin in office hours for this week. I hope you all have a good weekend, and I will see you on Monday.